Hi, welcome to the session Space-Time Smoothing in R. So this is one of the 3 sessions that we will actually go look at the code and see how things are implemented in R. So in this session, we will use 2 simulated data sets to illustrate a few different scenarios where you might want to do small error estimation. So the first scenario is relatively simple. We have a spatial problem. We want to do spatial smoothing of the prevalence of a binary indicator. And then from there, we'll move on to a different data set where we'll start to look at mortality estimation. So in the second example, we'll look at how to do space-time smoothing of neonatal mortality rates. So it's a still relatively simple binary indicator. And for those 2 tasks, we're going to be using a function called fitGeneric in the summer package. And then lastly, in the last example, we'll be looking at space-time smoothing of under 5 mortality rates. So this will include a few different extra steps, such as the discrete survival modeling and combining different surveys. And in all 3 examples, we will be using simulated datasets so that they don't actually correspond to any of the real DHS data. And in the next lecture, we'll be looking at real data and revisit some of the similar commands and similar functions that we'll be discussing in this lecture. Okay, so as I said, the learning objective, we want to demonstrate how to do space and space-time smoothing of not only a generic binary indicator, as well as a more complicated ones like U5MR. And we will go through the comparison of different ways of getting the estimates of a simple prevalence metric. We'll compare naive, smooth, survey-weighted, or design-based, and smooth and weighted estimates. We're also looking at different components in a smoothing model and how to adjust them in the summer package. And of course, at the end of the day, we will be studying this example of U5MR, and we'll be comparing the direct and smooth direct estimates of U5MR. And just as a reminder, all of the codes and the documentations are available on the websites. And there are a few additional resources at the end of this PDF slides. In this lecture, we'll be looking at methods mostly discussed in the second and the third paper here. And the package we're using is summer, and there's a link to the summer package. And with that, I'm going to switch to RStudio and see how things actually work out in real action. Okay, so now this is the familiar look of RStudio. We have covered some of the basics of using R and RStudio in the previous lecture. And for this lecture, we will be, again, looking at this R Markdown file. And if you go to the website, you will see a HTML file that looks like what's on this lower right panel here. It will have a more complete explanations as well as both the codes and the readouts. Okay, so as I said, we'll be looking at 3 examples. And in all 3 examples, we're going to be using the built-in simulated datasets in the summer package. So I just started a Flash R session. And in this session, I'm going to first load some of the packages that we'll be using for these examples. So we're going to need the summer package. We will use, very briefly, a package called SP to plot the shape files. And we're going to be using the ggplot2 package for visualization. And for the purpose of this presentation, I'm going to use this package called GridExtra. So in the first example, we're going to be doing a spatial smoothing of a generic binary indicator. So the dataset we're going to be using is this dataset called DemoData2 in the summer package. So I will use this one line of code. It's data DemoData2 to load this data frame into the workspace. So we can look at the first few rows of this dataset, and it basically looks like something that you will get from a survey data. So you have the cluster ID, you have the household ID, there's a region variable, which corresponds to which cluster, which region each of the classes belong to. And then there are there are, of course, also survey weights and a strata variable as well. And then there are two additional measures. The first is a variable called age, which is a continuous variable, and then there is a tobacco.use, or short for tobacco usage. And this is a binary indicator that we are going to be smoothing or calculating the prevalence of in this example. So we can take a look at this binary indicator very quickly by this one of codes. That's table demo data 2 $, tobacco use. Okay, so there are about 8,000 zeros and 345 ones in this simulated data sets. Okay, so since here we don't have time variable in this data frame, the question that we want to ask is, how can we calculate the prevalence of tobacco usage by region? Suppose we don't have any information about the survey designs, and this data set just come to us with region and the tobacco use, these two columns, and this is a simple random sampling. Then we can use this simple function called aggregate that basically calculates the average of tobacco use, this binary indicator, over each of the region. So I'm going to use this demo data 2 as the data frame in this formula, and the function is mean. So it's just a simple average. And now I run this line, and I save the results to a data frame that's called naive. So basically what this does is just taking a naive average of the prevalence of the binary indicator, ignoring all the sampling design. So of course, because in this particular data set, we are looking at region-specific prevalence, and actually in this data set, we have the regions that correspond to the 8 provinces in Kenya. So one thing we can do is to see what they look like on the map. So the map we're going to be using is this spatial polygon file, again, already built into the summer package. That's called demo data 2. So you can plot this demo data 2, the geo file or the spatial polygon file, and this is what it looks like, and it's the Kenya admin 1 shape files. So from the naive estimator, one thing we can do is to fit a Bayesian binomial model where we can smooth over the prevalence over this map. So the way we're going to do that is use this function called fit generic. So this is a function in the summer package where we need to specify first of all data, which is demo data 2, and then a spatial polygon file, which is demo map 2, $geo, which is the polygon file, and then something called a adjacency matrix. So here I'm just going to use the pre-calculated version. So if you can check it out from on the console, it basically is a by A matrix with the ones corresponding to which areas adjacent to each other. And then we need to specify the response type. And in our case, our response is a binary variable. So the response type here is binary. And the response variable, so which column that we want to calculate the prevalence, is tobacco.use. And then we need to specify, of course, which variable correspond to the region IDs. And in this case, it's region. And here, since we have been ignoring survey design up to this point, I'm just going to specify the strata, weights, and the clusters to be null. And of course, I can specify the level of the posterior credible intervals that I want, which is 0.95. Okay. So what this does is basically it fits a binomial smoothing model on the data sets, again, ignoring the survey weights. So now I run these 2 lines of codes, and it will take probably a few seconds to fit this model. Okay, so now this model has been fit, and I have created a variable called smoothed that holds all of the results from the fit generic function. So 2 particular data frame within the smooth objects are, the first is called smooth, which is basically the smoothing estimates from the binomial smoothing model. And another is called HT, which in this particular case, since we don't really have survey design, this is just a simple naive estimates. And later we will see once we specify the survey designs, this HT object will return the Harvey-Thompson or the direct estimates. Okay, so this is what these two particular data frames look like. Okay. So if you're interested, you can also check out the details of this fitted model, this smoothed. Okay, so if you spell summary correctly, here we are. So the smoothed object is basically a list that contains a few different things. The two data frames that we just talked about, the smooth and the naive, or if you specify survey design, the weighted estimates. And then there is a fit object, which holds the model outputs. So one thing you can do is to, again, look at the summary of these fitted objects. So I will do summary smoothed $fit, and it gives me some of the more details of the posterior distributions of all the parameters in this model. So in this particular case, we have an intercept, which is the overall level. And then we have a region.struct, which is a BYM2 model. And BYM2 model is basically a reparameterization of the familiar BYM model that have been covered in the lecture series. And from here, you can get the posterior summaries of some of the hyperparameters, such as the precision, the marginal precision of these random effects. You have the mean, standard deviation, quantiles at the modes as well. And then there is a phi variable, which corresponds to the proportion of the variance explained by the structure parts of the BYM model. And you can see in this particular case, it's not that high, it's about 0.3 in the mean and 0.25 in the median. So if you're interested in understanding a little bit more about the fitted object in INLA, this particular object, smooth $fits, there are a few other different things inside it. And if you're adventurous enough, you can go inside and plot a lot of different things as well. For our particular example of use of calculating U5MR in the later lectures, I will also show you how to plot some of the random effects and what they look like using the functions in the summer without going to the wonderland of INLA. Okay, so up to this point, we have ignored survey design. So if we take into account the survey designs, and we have looked at this already in the previous lecture, that you can calculate the weighted estimates by telling the codes of the functions a few different things. So here, in this part of the codes, we calculate the design-based estimates or the direct estimates in the small error estimation context. So here, we will first load this package called survey, and then we specify survey design. And within the survey design, we need to specify the IDs for the clusters and the variables for the survey weights, the variables for the stratas, and of course, what data set we're using. Okay, so here we have specified the survey design. And again, since we want to calculate the prevalence of tobacco usage by region, we can do the survey by commands. And using instead, so it's very similar to the aggregate function before, but here we're using this function called survey mean, which basically gives you the weighted version of the prevalences in this case. And then you can look at the first few rows of this data frame that we just created called direct. And it gives you similar output that has the region, tobacco usage, and standard error. So, and those are the design-based estimates and the design-based standard errors accounting for the survey designs. Okay, so with the weighted estimates, another thing you can do from these points is that, of course, you can also smooth over those direct estimates so that hopefully your estimates can borrow information across each other when we know what particular spatial region they belong to. So we're going to be using the same function as before for this smoothing model. To fit this smoothing model, we're going to be using this fit generic function. So the first few arguments are exactly the same as before. And we're here only specifying a few more, actually 3 more arguments, and those are the strata variable, weight variable, and cluster variable. And the way we specify those variables are exactly the same as what we will do when we're specifying survey design using a survey package. So we specify the strata, weights, and again, this is a 2-stage cluster sampling. We're going to specify cluster ID plus ID. Okay, so now we run this model, and it will fit this smoothing model on the direct estimates. And if you go, of course, if you go to the online HTML file, you'll see more mathematical details of what this function, what this method exactly does. Again, down in the smooth and weighted estimates section. And we have covered that in the other lectures as well, so I won't go into too much details here. Okay, so once you have fitted this model, you can look at this object that we have created that's called smooth weighteds. And again, there are 2 data frames that are created in these outputs. The first is HT, which stands for the Hurwitz-Thompson estimator, or the direct estimates. And another is the smooth. And again, in both those data frames, you have the estimates on the logic scale, as well as the estimate, standard deviation, variance, precision on the logic scale, as well as on the original scale, the probability scale, the estimates, variance, and in the smooth estimates, also the posterior credible intervals as well. Okay, so now we have fitted these 4 different models. These few lines of code basically combines them into a same data frame. So I'm going to quickly run these lines of codes, which basically takes each of those estimates that we just discussed, and those estimates as well as the variances, and assign a label that's naive, smooth, weighted, and smooth estimates, with smooth weighted estimates here. Okay, so if we look at this prevalence, the pref variable that we just created, it has a region, mean, variance, and which type of estimates we're looking at. Okay. So now we can visualize those estimates on the map and see what exactly they do in terms of estimating the prevalence in the space. So I'm going to use this map plot function, which we have seen before in other lectures. And again, we need to specify the spatial polygon files and a lot of other things. So here we have the estimates, and you can see that if you compare the naive and the smooth estimates, the second one, the latter, has a little bit smoothing over space, so you don't have that large contrast here. And the same thing if you compare the weighted and the smooth weighteds, the smooth version is, as the name suggests, always smoother. And we can also compare the variances of the estimates as well. And you can see that, just as we have shown in the lecture series, that after the smoothing, the variance of the estimates typically are much smaller than before the smoothing. So if you compare smooth to naive, and then smooth weighted to the weighted. Okay, so this is a case for a simple spatial smoothing. So in the next example, we'll be looking at a space-time smoothing scenario. So in this example, we're going to be looking at a different data frame, again, already built into the summer package. That's the demo data. And if you just do a quick summary demo data, you will see that this is a list of the data frames. which corresponds to, again, 5 simulated surveys from 1999 to 2015. Okay. So we'll be using, for this neonatal mortality rate example, we'll be using just one survey. So I'm just going to subset that and call it data. And here you can see that the data looks exactly like the person-month formats that we have we have calculated before ourselves. And before we move on to actually calculating under 5 mortality rates, which include a lot of other modeling components, here we're only looking at the neonatal mortality rate, which is basically looking at any of the person months that's within the first month since birth, or in this particular way, particular notation here in this data set, age equal to 0. So just as the illustration in this example, we're going to subset our data to be only those with age group equal to 0. Okay. We can check our data that looks exactly like what we were hoping it should be. Okay, so now this data set is very similar to before. You still have cluster ID, household ID, weights, strata. The only difference is that now instead of just region, we'll have region and a time. And then the question here is, can we estimate region time specific prevalence of the neonatal mortality rates, which is given to us by this column called DITE. So if you do a quick summary of this column, you see that there are about 1,000 cases altogether, 1,000 person months altogether, and about 47 deaths in this particular data set. Okay, so we're going to be fitting a space-time model using exactly the same function as before, this fit generic function. And in order to fit the model where we have a temporal component, the first thing we need is a index variable that corresponds to which time period is the first, which is second, because in this particular data set, our time was given as those 5-year periods. And without telling which one goes after which, there is no way for the code to know the correct indexes of the time variables. So I'm going to first create a variable called time.id. And you can see that the data now has another column, which basically says that for this particular time periods, it corresponds to the 4th time periods in all of the data. Okay, so now I'm going to, again, use the fit generic function. Again, we need to specify data, the spatial polygon files, the adjacency matrices, response, and a few things more from before. Now we specify a time variable, time bit, and in this case is what we just created, the time.id, and we can specify what temporal model that we want to fit. And right now in this function, we can fit a random walk 1 or random walk 2 random effects on a time dimension. And then we need to specify how do we want to define the space-time interaction term. And in this particular case, I have specified it to be the 4th type of space-time interaction. And as we have discussed in the lecture, this basically corresponds to an interaction of the time components and the BSEC model, or the ICAR model. Okay, so now I'm going to fit this model. It will take a little bit more time because of more random effects we're using, as well as this 4th type of space-time interaction model. Okay. So now this model has been fit, and we can look at the results. Again, we will just pull out the direct estimates or the HT outputs in this fitted object, as well as the smooth estimates in this fitted object. Okay, so I'm going to run these few lines of code, which basically constructs this data frame of the estimates, as well as making the time into a factor so that I can easily plot them on the map, on the plots. Okay, so now let's look at what the results are. So this data frame that we just created, I call it an MR, and I'm going to use this ggplot function, which I'm going to plot the points, the lines, and for each of the regions, I'm going to create a different panel, and I'm going to put the legends to the bottom. And this is what it looks like. So we have 4 regions in this particular data set. We have central, eastern, northern, and western. And we have the neonatal mortality rates. The red lines correspond to the direct estimates, and the green lines, or the more smooth lines, corresponds to the smooth estimates. And time periods are ordered from 85 to 5-year periods starting from 1985. Okay, so one of the things that we will actually discuss a little bit more in the following lecture is that if you look at this plot closely, you can see a lot of the direct estimates are exactly 0 because we have no deaths. Remember, we only have 47 deaths in this particular data set. So this is not exactly a great way to fit this model, because if you don't have a direct estimate in those periods where you don't have deaths, then essentially those smooth estimates are based only on the estimates that are either neighbors in time or neighbors in space. So we have a lot of smoothing here going on. And later in the next lecture, we'll show how to kind of overcome this problem using a binomial model. But for now, we'll just look at the smooth and direct estimates, and this is what it looks like in action. Okay, so this is it for the NMR example. Our last example is a lot more complicated. So this is our final example, final type of example. So we'll be looking at real data to calculate U5MR in the next lecture as well. So here we'll be looking at the space-time smoothing of U5MR. And here we're going to be using, again, the demo data, but we're not going to be using just the first survey. We're going to be using all of the surveys, and we're going to try to combine them together and perform smoothing for the combined estimates. Okay, so first of all, there are a few new functions that we will introduce in this section. The first function is called getDirectList, which basically is a wrapper for the getDirect function that calculates the direct estimates that we have seen in the previous lecture. But here we're calculating direct estimates for a list of multiple surveys. So here in these two lines of code, I'm going to first save something which I will be using repeatedly in the next few lines of code, so it's a little bit easier to write them, which is the years variable. And what it does is basically saves those, in this particular case, 6 different periods, since we'll be using those for fitting the models repeatedly in later sections. And then I'm going to use this getDirectList, which basically works the same way as the getDirect function that we had seen before. And I'm going to save the results to this data frame called data_multi. So this will take a few seconds to run, and now it's done. And if you look at the first few lines of this data_multi data frame, you can see that there are direct estimates. So again, we start with a national estimate, so the region equals all. And then for each of the years, we have the means of the U5MR, lower and upper bounds, logits, and there is also this column called survey. So we start with the first survey, and you can see that if you go to the last few lines, we have the estimates for the 5th survey. So this is a pretty big data set where you have survey-specific direct estimates for both the national and subnational regions. And you can check that by the dimension of this matrix. Okay, so this is quite big. So in order to fit our smoothing model, we actually need one set of direct estimates. So we will use this function that's called aggregate survey. And what it does is it basically creates a meta-analysis type of estimator where we combine those estimates from different surveys into single estimates using their weighted average, and their weights are given by the inverse of their variances. Okay, so now this data frame have dimensions 30 and 10, and again, this looks similar to what you will get if you just have one survey and fit the get direct estimates. Again, you have the means, lower and upper bounds, just as before, and then now the survey variable was turned into NA because all six surveys have been combined into this particular data sets. Okay, so after combining these direct estimates from multiple surveys, we now will discuss how do we fit smoothing models for both the national and subnational estimates in the next few minutes. And in each case, we are actually going to discuss two different smoothing models in terms of how do we actually fit the temporal trends. So let's start with the national estimates. So in order to fit a model for the national estimates, basically we're just ignoring all of those direct estimates for the subnational regions, but just use the direct estimates for the national levels. So first of all, we're going to use this function called fit inla, which will basically take the direct estimates and then, of course, a few other arguments, and then gives you the smooth estimates and fit the whole Bayesian smoothing models under the hoods. So a lot of times we're also interested in projection into the future, and this is what I'm doing here. So I'm creating a new variable that's called years.all, which basically is the same list of the years plus one period forward. Now I can use fit inla to fit this model, and we're going to use we're going to need to specify the data, which is the combined version of the direct estimates that we just created. And since we're fitting a national model, we don't need to specify any of those two arguments. And then we will specify the year underscore label variable, which is what we just created. And here we're going to specify the random walk, and we're going to specify it to be random walk 2. And we're going to specify a non-yearly model. And since we're working with a national model, we don't need to specify type.st. Okay, so I haven't said exactly what this is.yearly argument does in terms of fitting the model, and we can actually see in real action very fast in a couple of seconds. So here I fitted another model using almost the same type of arguments, except now we specify a few different things. I specify year underscore range to be 1985 to 2019. So just the two ends of our observation periods, or the periods we want to make projections on. And I'm still using the random walk 2. And now I specify is.yearly equal to true, and there is another argument, m equal to 5. So m equal to 5 here basically says that for each period, it contains 5 years. And then what this lines of code does is that it estimates a smoothing model, again, space-time smoothing, but instead of saying that we're going to put a random walk, in this particular case, random walk 2 prior on the periods, now we're going to put a random walk 2 priors on a random effects that are defined on the yearly scale, and all the period estimates are just the average of the random effects in the corresponding yearly scale. Okay, so now I have fitted both of these models. In order to compare the results, I'm going to invoke another function that's called getSmoothed. And it's actually quite easy to use. You just use getSmoothed and followed by this fitted object, and it will gives you a data frame that contains the smooth estimates fitted by this model. So now we can compare these two different models. Again, use And we'll first look at the figures here, and then we'll tell a little bit more about what the visualization code does. So here you can see on the left-hand side, we have the period model, where we only have a random effects on the period scale. So we have, in this particular case, 1, 2, 3, 4, 5, 6, 7 periods, so 7 random effects corresponding to the time dimension. And in this case, we actually have yearly random effects, and the ones in red corresponds to their averages or the period estimates. So we can actually obtain we can actually calculate some sort of yearly estimates under this smoothing model. Okay. So again, since as we know that the last period is the projection, we don't have any data over there. So here in this figure, those are represented with these dotted lines at the end for the projected periods, as also showing up here. Okay, so in order to get those visualizations, if you obtain your estimates using the getSmooth function, it will create a data frame that within Summer it will recognize as smooth estimates, and you can very easily use just this plot function on these objects, and you only need to specify whether or not this is a subnational estimates or national estimates, and then a lot of the internally a lot of things have already been set, so that it gives you either for the period model that look something like this, or for the national yearly model, the estimates over time with the period highlighted in red. Again, the object we created here is ggplot objects, so you can easily specify additional themes or scales or many other things, such as the limit of the y-axis and the titles here, as I'm doing. So it's relatively easy to customize once you have the figure. Okay, so this is how do we calculate national estimates of U5MR. Now we're going to move on to calculate subnational estimates. We're still going to use the fit-in-law function, and we're going to need to specify a few different arguments. So basically the spatial polygon file geo, and we know we're using the demo map, so we're going to be using demo map $geo, and then we're going to need to specify the adjacency matrices. And in this case, the adjacency matrix in this demo map is just demo map $amat. So again, in the next lecture, we'll see how we're reading a map and calculate adjacency matrices directly. But for now, since it is already built in, I'm just going to directly use this amat matrix here. And again, we need to specify year label, random walk either 1 or 2. And then here, as before in the neonatal mortality rate example, I will specify this type.st argument to be 4, which correspond to the type 4 interaction model for space-time random effects. So again, we can do this for the period level or for the yearly level. So I'm going to fit these two models separately. So first I'm going to create this fit3 object, and this is for the period model, so is.yearly equals to false. And then again, I'm going to use the getSmooth function to obtain the smooth estimates. And in this particular case, I will need to input what is the adjacency matrix in order to get the correct labels on the outputs. Okay, so now this has been done, we can fit the yearly model. Again, similar to before, you need to specify for each period how many years it contains. In this particular case, it's 5. And then we're going to use the getSmooth function to get the smooth estimates, and we need to specify the amat in this particular function. And once that is done, I will just plot something very similar to here, but instead for all of the subnational estimates, and in this particular example for subnational regions. And you can already see from the codes here that the only thing we need to change is that is.subnational equal to true. So now we'll run these few lines of codes. And I will plot them together on top of each other. Okay, so now you can see that we have 4 regions: Central, Eastern, Northern, and Western, and the yearly model and the subnational model. And because there are too many lines here, and if we plot the quadruple intervals, they will overlap and make it a little bit harder to see. So by default, I'm not plotting the quadruple intervals here. But if you're interested, you can actually add them back. And of course, when we have a lot of confidence quadruple intervals here, we'll probably want to put them into different panels. And this is what I will show here. So this is for the yearly model. So I'm going to use, again, this plot function. And this shows some of the things this plot function can do in addition to just plot that one trend. So I'm going to use plots, call this function plots out for, which is the yearly model. And need to specify that this is, so in this particular case, I specify is.subnational equal to false, so that we don't really have colors for each of those subnational estimates. So they will all be in the same color. But what's interesting here is that I can use these following commands to add additional data to these plots. So here I'm adding date.add arguments, and I'm adding this data_multi data frame, which, if we recall, is basically the direct estimates for each of the survey-specific estimates. And then we can specify some of the options. So the variables we're going to be plotting here, or the variables that correspond to the y-axis in this case, in this data_multi data frame, is this column called mean. And we can group them by the survey years. So if we remember the heads of data_multi, okay, so the mean here is basically the direct estimates, and I will plot different groups of the direct estimates, and they're grouped by this variable called survey years, which corresponds to which survey the estimates came from. So of course you can customize the colors, whether or not you want to plot the quadruple intervals, and how transparent the intervals should look like. In this particular case, since we are spreading them out into 4 different panels, I'll just plot the quadruple intervals, and I spread them out using this facets_rep. And again, in this line codes here, I have set the scales to be free so that if you look closely, those y-axes don't exactly match each other. So one way you can do it alternatively is to remove that line of codes, and it will give you the similar plots with the same y-axis. Okay, so our final plot for this lecture is, of course, to put everything back on the map. So again, I'm going to use the map plot function. And I'll show you in a minute here. So if we look at this out for or the smooth estimates, you'll see that there is a column called is.yearly. So some of them are true. That corresponds to the estimates of a particular year. And if you look at the end of this data frame, there are also estimates that corresponds to false in this is.yearly column, and those are the estimates for the 5-year periods. Since there are really a lot of years here, I'm just going to show you quickly the maps for the for the estimates corresponding to 5-year periods. So I subset my data to be is to have the rows where the column is.yearly equal to false. And again, we're going to use the spatial polygon files. We're going to specify which variables to group by, which value to plot, and the columns in data and the shapefiles that correspond to the region so that those two can be merged together. And of course, 4 columns in this particular case. And notice that I use this per thousand arguments, so that's all the undefined mortality rates are scaled up by 1,000 births. So if you run this line of codes, as you have just seen on this panel here, you have the estimates for each of the regions over the periods. Of course, you can do a lot of other things, such as you can pick up specific years, plots, and you can add different things, that you can add hatching to it, as we have shown in previous lectures, and we will also see in future lectures as well. But this is basically how you can fit different spatial models, spatial and spatial temporal models in the summer package. So just to wrap up, in this lecture, we're basically looking at 3 examples, but fundamentally we're only looking at 2 different functions, which are get generic and the fit generic and fit inla, and those 2 functions correspond to some of the common space-time smoothing and in particular small area estimation tasks that we might find useful in calculating subnational child mortality rates, or in general working with data for complex, from complex surveys. So again, in this lecture, all of the data set we have used came directly from our package summer. So they're simulated data, so it really doesn't make a lot of sense if we go in there and try to explain and interpret some of the internal results. So in the next lecture, we'll be looking at real data, and we'll spend a little bit more time in making plots, looking at the fitted values, and as well as the posterior distribution of random effects, and try to interpret and see what they actually mean and how our model decisions affect the results at the end. And with that, I will wrap up this lecture on space-time smoothing in R. Thank you.